So if S plus or S minus exceed a control limit H, then the process is out of control, where S plus detects increases and S minus detects decreases. As before, it's useful to look at control limits. And before we had the 3 sigma control limits. And so we again express that as a multiple of sigma. This is a different multiple of sigma than the K. The K was used to understand the alternative hypothesis. This is now for a multiple to understand the control limit. The problem is that when we have a single observation or a single batch, then the normally distributed assumption allows us to interpret what a 3 sigma control limit means. And we don't have that right now because we have the score includes the current value and all the past values. So what we do instead is we choose the multiple of sigma H to yield a desired average run length until false alarm is raised. So that's analogous to our thinking when it was normally distributed and we get 3 errors in 1,000, that corresponds to 3 sigma. And so now we have to figure out what the average run length is again, and we will talk about that a little bit more later. But broadly speaking, for wide ranges of average run length and choices of K, H is between 4 and 5. And to give one example, to detect a mean shift of 1 standard deviation, meaning K equals 0.5, with an average run length of 374, which is similar to the 3 errors or 2.7 errors out of 1,000, H can be determined to be 4.76. Okay. So let's look at the control limit for the data for the example. The CUSUM chart was on the left. Here we have the S plus and S minus. S plus is here in green, S minus is in orange, and you see the control limit. We get once close here, but only close. There, it's not quite. Here we raise an alarm, right? So that's fairly late. It's after 800 observations, more or less. 180 observations. But we also didn't use the optimal K because K is 0.5 that guards against a 1 sigma shift. But we know because we did the simulation that the shift was smaller, was 0.2. And that's the reason why we get the alarm so late. Now, we could say, well, if I know that the shift is 0.2, why don't I construct the control limit such that the test is optimal against a shift of 0.2 sigma? And we will do that in a second. But the reason why I didn't do that initially is because I didn't think it was fair. It's a simulation. In a simulation, I know everything, right? And it's easy to find something optimal for a simulation. But on the factory floor, I don't know what exact mean shift is going to occur ahead of time. And so I have to make a reasonable guess of what I want to guard against. And so I wanted to use the 1 sigma instead. All right. But if I knew it was 0.2 sigma, that's a very, very small shift, right? So if I'm wrong on that, then I'm going to get lots of false alarms that I don't want. Then I can figure out the optimal values. And so here's a question for you. What should be changed to guard against a mean shift of 0.2 sigma? Just K or K and H? I will leave you to ponder this and move to the next question, which sort of gives away the answer, to be honest. But here we have the CUSUM chart again, And now we have the cumulative score with a control limit. This is different now. We have different values for S plus. We have different values for S minus because the slack changed, right? And so when the slack changes, all the values of the scores change. Control limit, of course, changes also. And we are using here 4.76 nonetheless, because we know it has to be between 4 and 5. Okay, so where do we get an alarm? We get an alarm here at about 40, right? That's pretty good, because the change only occurred on 20. So we're getting an alarm at 40. That's pretty good. And if we let it run, it continues to give an alarm here, right? Now, for the S minus, we're getting close once to an alarm. It's not quite there, but it's close. But remember, we have here 200 observations, so 200 times we're testing this, and then we had another 200 times here. And we get one false alarm every 370 observations. So from that point of view, it's not all that surprising here, right? So that we're getting close, or we might have even gotten over at some point. Okay, that concludes this segment.